Okay, so can you hear me? Usually I speak without microphone, so need to adjust my voice here. All right, so let's continue talking about the hot topic of BE stars. So the first talk by Alex was more theoretical introduction, and then the talk probably tomorrow by Aaron is also going to be theoretical. Mine is mostly observational. So here is a team. The first three people are on the faculty of the University of North Carolina. And we work at the observatory, which I showed last time and I think the first time, but I will remind you about our observing place. It was designed by now retired Professor Stephen Danforth in the 70s. In about 2011, it became a real research facility with spectroscopy. Then we hired a younger astronomer who, I don't know if she gonna... It doesn't work. Yeah, it doesn't work. Yeah, if she gonna keep the observatory moving or not, because some of you know that our department is supposed to be closed in a few years. But we may actually try to fight. And then I have some colleagues. One of them is Sergei Zharikov, who is working in Mexico. And he is, by the way, is an expert in Doppler tomography. His main topic is cataclysmic variables. And now we are trying to apply this technique to reveal some, at least part of the structure of the circumstellar disks in BE stars. And our great helpers are young PhDs and graduate students from the Kazakh National University in Almaty in Kazakhstan. So this is our team. And just a little bit about history. So this is my fourth talk at the VEGA conferences, and I typically talk about BE stars or B bracketed stars. B bracketed stars are different from BE stars by the fact that they have dusty circumbinary disks. And now I'm surprised that Alex told us about formation of circumbinary disk in BE stars, but perhaps there is not enough material to start forming dust there. So who knows? Maybe those dusty parts of the outer circumstellar disks in BE stars will be discovered. It just may be a problem of sensitivity in the infrared. Anyway, so I'm coming back to BE stars because it's one of my favorite topics, and I started studying those stars while I was a postdoc at the University of Toledo in Ohio, and I believe Alex did that too, because we intersected for some years over there. And for today's talk, the outline is just a little bit about our spectroscopic program, which was growing significantly since 2020, when our observatory became fully automatic. Then I will show you some results on pretty bright BE stars, fourth, even third magnitude, where we are studying the disks. Then we have some recent interesting results on the V/R variations. So V/R, remember that these are ratios of the intensities of the double peak profiles, which are typical for disks. And we found some in-phase phenomena which are going on between radial velocities of absorption lines, which belong to atmospheres of the main B-type stars in the BE binary systems, and those V/R variations. So show you a little bit about Doppler tomography with a little introduction to it. And then we'll get to the future. Okay. Alex did some introduction on how disks form, how material gets out of the star, and this is just, again, a very little introduction to what is going on in normal stars. And in my terms, normal stars are those which don't have much circumstellar material. So it is there. For example, the sun is surrounded by all those planets and asteroids and comets. But if you look at the sun from outside, then you will see the atmosphere. So you won't detect that circumstellar material unless there are some transits of planets in front of the disk of the sun. So the spectra of normal stars, they form in the atmosphere. So the photosphere, the green part, sends out a continuous spectrum. Because of a high density, all the lines blend together, forming a continuous spectrum. And then in the atmosphere, due to the structure of various atoms, only photons with certain wavelengths get absorbed, and they form those absorption lines, and the strengths and the widths of the absorption lines depend on the fundamental parameters of stars, which are the photospheric or effective temperature, then gravity, and the rotational velocity. So here is just a sequence of various temperature stars from famous now atlas of Richard Gray, who works at the University of North Carolina as well. So these are normal stars, and this noise which you see here at lower temperature stars, these are simply neutral metal lines which are real, and depending on the spectral resolution, you can either resolve them or not. Then what is going on in the circumstellar envelope? There is, typically we talk about hydrogen because hydrogen has the best known structure of the atom, but for this purpose it doesn't matter. I just list some wavelength, ionization wavelength for hydrogen. So photons coming out of the atmosphere, they hit atoms in the circumstellar material, and atoms become ionized. So electrons get out, gaining some energy. But after certain travel between other atoms in the circumstellar envelope, the electrons get captured by another atom. And then that capture can occur at different energy levels. So when the electron is captured at some level, it gives off some random parts of its energy. And this, because there are so many processes like that going on at the same time, it adds to the circumstellar continuum. So if we have a noticeable number of atoms in the envelope, then some additional continuum will be produced. For B-type stars, it's typically adds some reddening, circumstellar reddening. But then, after first capture, electron goes down energy levels, and as a consequence of the law of energy conservation, photons with the frequencies or wavelengths of those differences of energies, they come out, and this is the source of formation of spectral emission lines. So the circumstellar radiation is essentially a transfer of energy from ultraviolet, X-ray wavelengths to optical and infrared. And then it the emission line profile depends on the structure of the material around the star. So if it's more or less spherical envelope, then you will see a so-called P Cygni profile, which has some emission on the red, shifted to the red of the central wavelength of the line, and some absorption which is shifted to the blue, because it shifted to the blue because there is higher optical depth in this region between us, in front of the star. For the disks, it works like this. So depending on the tilt angle with respect to the line of sight, the Doppler effect works. And if there is enough material moving away from us on one side of the disk and towards us on the other side of the disk, you have the double peak profile. And the strength of the profile will depend on the tilt angle. And if we observe a star polon, then there won't be any split because, again, all the motion goes on in the plane perpendicular to line of sight, and the Doppler effect essentially doesn't work. There is this central depression. Again, I'm just introducing a little bit of terminology which is not generally adopted, so some people call it central absorption. This is not an absorption. This is just a lack of emission. So there is more emission in these areas on the sides, which give rise to the peaks, and less emission in front of the star where the central depression forms. But in any case, this is just the basics of formation of emission lines. There is fast rotation. Again, all B stars are rotating fast, but then it depends also on the tilt angle. Sometimes you observe the star towards the pole, and in this case, we see mostly the polar regions. So gravity darkening is not actually changing the spectrum much. Again, because Alex has introduced that, I just had that slide showing that now we think, or kind of more generally adopted explanation to the reason for decretion for launching those particles from the atmospheres of B-type stars into orbits are two main reasons: non-radial pulsations. And this is what you see when you look at the photometry from those bright satellites. So these are small satellites flying in space and targeting pretty bright stars, typically second, third, fourth magnitude. And because they are in space, the precision is very good. So it's in millimagnitudes. You can see that it's 10 millimagnitude, 20 millimagnitude. And this is a reflection of non-radial pulsations because you can judge that by the period. So period is around 1 day. So rotation, fast rotation, and non-radial pulsations make the material to get out of the atmospheres. But there may be an additional reason, and this is binarity. So it was a long story that originally B stars were thought to be just fast rotating, and nothing was known about binaries. Even by the end of the 20th century, we knew just a few binary B stars, but now with ultraviolet observations, with massive spectroscopy, and the amateur community is helping significantly in revealing those binaries, we can detect the presence of the secondary, which is typically much fainter than the primary component, by indirect effects. Direct effect would be more radiation in the ultraviolet, because some of those secondary components are hot subdwarfs, stripped cores of stars, most of the material from which was transferred to the current BE star. And indirect methods include radial velocity variations and VOR variations. There are some problems with dealing with BE stars because they rotate fast. their spectral lines from the atmospheres are wider. And here I show a comparison of two spectra of stars of about the same temperature, but very different rotational velocity. So Gamma Pegasi is a B-type star, not a BE star. And you see that because of its low rotation rate, the lines are narrower and stronger. And 66 is a binary BE star with rotation rate 10 times the one in Gamma Pegasi, and the lines are definitely much wider. And if you have relatively low resolution spectra, then those weak lines, they blend together. Even strong lines can blend with surrounding lines, and it's much more difficult to measure radial velocities of those stars. And Achternaar, again, is a kind of another picture of a typical shape of a fast-rotating B-type star. Okay, so why do I have it here? I'm trying to get rid of all these additions, but forgot for that slide. So when now generally accepted explanation of most B stars, and in recent papers people say that most, if not all, B stars are binaries. So what can we get out of observing binaries is that spectra give us orbital periods. If you have, again, ultraviolet infrared spectra, you probably can learn something about the secondary companion. And by the way, you don't need to observe that helium-1 1080 1 micron 0.08 line. You can do that helium-6678, for example. Sometimes it comes from the secondary component, and that line moves in anti-phase to the hydrogen lines. So, but it depends on the nature and the brightness of the secondary companion. Then we can learn something about those binaries through infrared excesses. As a matter of fact, because they're binaries, we can catch them at different evolutionary stages. So some already ended the evolution, and as a result, the secondary companion is that stripped O-type in most cases, or B-type dwarf. But during the evolution, the secondary star can be a cool star. I think, I don't remember any clearly detected such cases, but we recently started suspecting some. Anyway, just because those cool, if the secondary is a cool star and much fainter again than the primary, it's really hard to detect any spectral lines from it. And then again, as Alex showed, that secondary companion can get some material from that disk. And by the way, you correctly remembered, Alex, that the first star where we got it was Pi Aquarii, and I have that slide, but at that time we were not sure. We didn't have any theoretical support for this conclusion. Now, how to find those binaries? Because again, you see just one star and some signature or signatures of the disk. Obviously, it's periodic radial velocity variations with right periods, because you see that there is non-radial pulsations, and you can find frequencies around the period of a day or less than a day. So these are definitely not orbital periods. So orbital periods start from at least a few days, but in many cases it's a few weeks. But those orbital periods can be several months. Like Gamma Cassiopeiae has an orbital period of about 8 months, and can go even to 2 years. And then recently it turned out that those V over R variations can be phase locked with the material. So some stable spot or spiral moves around the B-type star and causes the change of the intensities, the periodic variations of the ratios of the intensities of the blue peak and the red peak. And this is just because in the 20th century, B stars were not observed as frequently as they are observed now. So that's why we keep discovering new binary systems, even when we cannot detect radial velocity variations. So it turns out that V over R variations can give you some properties of the binary. So before we started analyzing the results of our program, which I will describe in a minute or so, there are only 5 binaries known with phase-locked V over R variations. So those V over R variations occur with the same period as the orbital period. Then there are some other complications. It turns out that if the B stars are weak-lined, and again there are several examples shown in Alex's talk, it may mean that they only started forming new disks, or they're getting rid of the disks, and this period of evolution of the disk can be pretty erratic. So there may be no period detected because it always changes. And then if there is a lot of material in the disk, the strong-lined B stars, they can show longer periods. So there are some stars like 48 Librae, which has a period about 20 years. So you see those variations of the peak intensities of the origin lines, but again, the period is very, very large. So there is some range of B stars where at least this method can be used. So some intermediate range or B stars with some intermediate amount of material in the disk. Okay, so now I'm just coming to a little introduction of our observatory. It is located here in the state of North Carolina, in the middle where those NC letters are. And this is a Google map with the precise location of the observatory. I live here, and our university is located here. And there are 3 big cities. Charlotte, which has a population of about 1 million people, maybe even more now. Raleigh, the capital of the state, where about 600,000 to 800,000 people live, and Greensboro, where about 300,000 people. So these are big light polluters. And when the observatory was being designed, when people started looking for a place, they were thinking about the future. So the initial planning was done in the middle 1970s. And they came up with a location on a little hill in between those cities, and it's still dark there. So if you go there on a clear night without the moon, you can see the Milky Way. You can definitely not see the Milky Way from those cities and even from the other little townships in between. So this is our latitude, which allows us to see a pretty big chunk of the southern sky. And I was always interested in the southern sky because I was born in St. Petersburg, which has a latitude of 60. I didn't even see the entire Canis Major. So this is a window for me into southern sky. And the altitude of the observatory above the sea level is pretty low, but it helps us with having almost no cosmic rays. So they all absorbed above us, and they don't hit the detector. So here is a modern view of the observatory. If we have time, I can show a 9-minute long professional presentation about our observatory, but maybe sometime later. This is a weather station and all-sky camera. There is little parking for the public because in addition to science, we do some public shows. And here is our dome. It's not very compact because, again, it was built in the 1970s, but it's totally automated. And it takes the astronomers from our city about 45 minutes to get there by car. So this is south, and recently some trees were removed from there. So now I can observe down to about minus 40 degrees declination. Yeah, almost. We're like Brazil here. Okay, good. So that's our telescope. I think this picture was taken before automation because there are not as many wires there. So this is the guiding unit for the shell spectrograph, which we got from the Shellyak instruments, and these are optical fibers. So, and this, by the way, is an old flat field calibration screen for photometry, but we don't have photometry, we don't use it anymore. Okay, so our observing program, in addition to getting interested in B stars, I've always been interested in B Bragg stars, but unfortunately, and I don't know for what reason, there are not many around us. There are just a handful of them closer than 1 kiloparsec from the sun. And as a result, we can observe like 5, 6 of them down to about 10th magnitude. And that's the limit of our telescope with the spectrograph, taking into account its size. We started observing program in the end of 2011, pretty slowly because before 2015, the telescope was operated on a old IBM PC 486 machine, which young people don't even know what it was. Then in 2015, we got in contact with a company called Sidereal Technology. So there is a person there who actually, in addition to producing some software for sea vessels, he is an amateur, astronomy amateur. His name is Daniel Gray. So he automated our telescope in terms of pointing, and then in 2019 he also did full automation of the observatory so it can be run remotely. So B star program is the largest one, and here you can see how many spectra we've got for certain bright stars. And recently, with help of students, we started analyzing those stars. That list is not full, and we are trying to increase the number of spectra for those stars, which will allow us to figure out whether they're binaries or not. Some of them are known binaries, but some of them have information about orbital periods which is incorrect from long past, and will definitely need to be revisited. All right, so first example is Nu Geminorum. It's a 4th magnitude star in Gemini. So here, I might have shown this slide last time. So most of the time, the H-alpha line profiles are double-picked, and you can see the VOR variations. So here the red peak is stronger, here is the blue peak is stronger. But there was a period of time, by the way, when we, with Alex, worked together in Toledo, the line profiles were triple-picked and quadruple-picked. So now we need to explain that. There has been no explanation to that, but it was very short period. And at that time, the VOR variation was fluctuating significantly. And when a group of researchers on B stars led by Thomas Revenius from the ESO did that analysis, they detected an orbital period by measuring radial velocity of one line, of helium line. But they were not able to detect any periodic VOR variations. And they concluded as a result that the B star is the 3rd companion of a triple system. Again, this conclusion was done pretty recently, in 2021, and it was supported, the triple nature of this system was supported by astrometric observations because they resolved that 3rd companion. But they concluded that it was a B star moving around an inner binary. And our data showed that the spectral lines, the absorption lines from the main star, B star, and VOR variations move in sync. and it actually alters this model. So B star is not this one, it's one of those. This may actually reconcile some problems between the spectroscopic and astrometric solution, which different groups came to when it turns out that it's really hard to reconcile the two. Anyway, what was new here is that, so this is the phase diagram for the radial velocity, so those lines moving back and forth. Unfortunately, the system is tilted so that the rotational velocity multiplied by the sine of the tilt angle makes lines narrower. Because if we observe it, if we observed it through the disk, then it would have been full rotational velocity, which is over 300 kilometers a second, and some of those lines would have been blended, and it would have been harder to determine the radial velocity. In the middle, we show that there is a little difference between the elliptical solution for this phase curve and circular solution. So it's very little, but it's statistically significant. So there is some eccentricity to the orbit of that inner binary, which may be induced by the third companion. And what is here is the V over R variations. We just go in sync. It simply means that there is a stable spot in the disk which follows the secondary companion, and it is going on for a pretty long time. Now notice that the amplitude of the intensity ratio variations is not very large, so it requires pretty high signal-to-noise ratios, and there is some scatter because there's probably some additional inhomogeneities in the disk. So this was the first star where we got that result of the in-sync radial velocity and V over R variations. Then we looked at our collections of other stars, and here is Epsilon Capricorni, which is also a pretty bright star. And here we have that wave. The orbital period is, by the way, much longer. So this is a previous determination. This is our, and I think our period is a little bit better because we have a longer timeline. But it's pretty noisy. So this comes from helium and magnesium line at 4471, 4482. But it turns out that a much better phase curve comes from the central depression. So Alex told us that central depression is an indicator of the systemic velocity. But it turns out that it can move.
It is not always.
Yes, exactly. And that's why I'm showing Psi Persei here, where it doesn't move. Yeah. So we probably need to figure out why in at least this star, I think it's the only example. So the line, that core of the central depression moves with the orbital period, and in others doesn't. But again. And here is the V over R variation. So lots of noise, but the Fourier analysis and the folding the data with the orbital period shows that definitely it is there. So it's also phase locked. Then there is a very good star, Kappa Draconis, because it is located, not for you, it's only for us, plus 70 degrees. So close to the pole. I think it's about the most northern B star, so it can be observed all year round from northern locations. And it has a very similar spectrum, a little bit larger projected rotational velocity, but we were able to do cross-correlation on this part, and we got pretty nice period, which actually confirmed previous findings from the 19th and early 2000s. So it's about 2 months. But then we did the analysis of the intensity ratio, again, when you look at just the temporal dependence, then without any Fourier analysis, any kind of any mathematical analysis, you wouldn't say that it's going to be periodic, but it's strictly periodic and it's in phase with the radial velocity variations. So we took this star and did Doppler tomography. So this is the basics of Doppler tomography, which was introduced in this paper in 1988, and it was applied to cataclysmic variables, stars with very hot and very cool components. Oh, yeah, this is number 2 pi. Yeah. So what you do, you just do this transformation. Gamma is the systemic velocity. This is the amplitude in in the x direction. This is the amplitude in the y direction, and this is the phase. So you need to have a good number of spectra at as many as possible phases. And with this transformation, you get a Doppler map. So in this Doppler map, these are lines of the equal radial velocity. And then it can be transformed into a real map in Cartesian coordinates, where radial velocities are this kind of closed circles. Now, if there is a spot, and again, this is an application to some cataclysmic, very short period binaries, that's what is going on in the spectra. So this blob is a denser one. It produces more light, and in this phase, when we see both stars, when stars do not eclipse one another or they are not on the same line of sight, this spot contributes to one of the peaks. When we observe it this way, this is the source of the central peak. But again, so this is just a sketch, and it was not applied to B stars. Kappa Draconis, back to it. So this is a sequence of spectra which we took over the years, so starting 2014, when the line was very strong. And it turned out that at that time the disk was dissipating. So by about 2022, it totally dissipated. So now if you take a spectrum of this star, you will see just a little bump there, which may be part of the circumstellar material around the secondary component, which I have not analyzed that. And when you apply that routine of Doppler tomography, again, it's kind of non-conventional view. So this is one component of the full velocity. This is the other component. The plus is the location of the primary star. The other plus is the location of the secondary star. But everything is outside in. So the farther away the emission is from the central star, the closer it is to the star. So it's inverted picture of the disk. But it showed, we did this analysis, we applied it to several different epochs. When the line was big like that, when the line was intermediate intensity, and when it was disappearing. And this spot was still at the same place. So it actually moves with the secondary component, which is here, as it moves around the center of mass. The center of mass is shown by that X. It is very close to the main star because the mass ratio is about 10. So the secondary component is about 10 times less massive than the primary component. So that was published probably last month. Anyway, so we decided to apply it to this guy, pi Aquarii. So this is a result from our old paper, 2002. We caught it in Toledo when the disk was dissipating. So from 1995 to 2001, this was the Chalfa line profile with a little peak, emission peak, moving from one side to the other, and this is the radial velocity of this peak. So this curve. Then I also measured how wings of the line move. And it turned out that that motion was like this in anti-phase. So this is this anti-phase picture tells us that this peak, little peak, belongs to the material around the secondary star. And if you subtract the contribution of the primary star, which is much brighter, that's what you would have seen in the spectrum of the secondary star, just something single-picked. Now, this slide illustrates how poorly observed these stars were in the last century. So from 1950 to about 1980, the disk was growing in this system. And then in 1989, it started declining, and in about 6-7 years, it disappeared completely. Then, for about 10 years, there was no disk. And here you see what has changed to the equivalent width of the H-alpha line since 2014. So it started getting brighter, getting stronger, and it almost reached about 40 angstroms in the equivalent width. So it was 30 in 2023, I believe. Now it's declining, but we lost the star because it's behind the sun. We will try to catch it in August or so. Now, this was our first Doppler tomography, which we did in 2013, and Sergey was the main author here. So here is VOR variations, which we, by the way, this paper was inspired by Ernst Pohlmann. That's why it's very sad that he cannot be here today. He collected, he did lots of observations with his RS group, and then some others from us were added there. And you can see that V over R also behave similarly. They're phase locked. And by the way, this shows another thing which we will need to explain better. When the disk was in its full glory with lots of material, there was a single peak profile. Again, it was interpreted as a single peak. But you see those shoulders here and there, which can make you think that it's probably some contribution from a central peak, which disappeared when the disk started disintegrating. So actually, I think in 1989, when this process started, the profile went from this to this. So some part of the material disappeared. So when we did Doppler tomography, we found that there was some bright spot or density enhancement in the disk around the primary component, which moved around it with the secondary. And this is the location of the center of mass. Which may be different now because some other group came up with a different mass ratio. We figured out the mass ratio from the amplitude of the motion of the line, of the absorption line in the primary component to the amplitude of the motion of this little peak. But this little peak may not correctly represent the motion of the star. Anyway, so it's still tells us that even very bright stars need further investigation. So now, this is a result which is in the making. You can see what the H-alpha line profile look like now. So this is a profile from our observatory from 2021, triple peaked. And here the third peak is more intense. And then we did Doppler tomography and came up with different pictures. So maybe this is a reflection of some S wave or some two spiral arms there. So we'll see when we analyze sets of data with different strength of the H-alpha line. And the first impression is that the third peak, this one, is responsible for one of the denser spots, and the other is moving again with the secondary companion. So that's in the making, but it's the second star where we applied Doppler tomography. To the boring star, binaries minoris. So, as Alex said, its disk is actually at about the same state. So the strength of the H-alpha line is about 1.8 at peak with respect to the continuum. And here I showed two profiles from our spectrograph, where in one of the profiles the red peak is a little stronger, in the other the blue peak is a little stronger. So when we had no many observations, we collected it from different observatories with different spectral resolutions, we came up with a period of about half a year, which is always suspicious. Maybe we just observe the star half a year, then half a year we don't observe it, and it may be that frequency which you can see in the spectral window, but it's not present there. Anyway, 183 days from the intensity variations. Then another group came up with a period of 170 days from moving the profile back and forth, the wings of the profile. And this result was questioned by a group of Czech people led by Peter Harmanis, who said that these changes are really tiny and they may be due to pulsations. Okay, over the years we collected more data, like about 200 more spectra, and we found, that this picture is stable. So this is what we got in 2014. And different symbols have, they show observations from different places. So these dots are from our observatory, and open squares from the Ritter Observatory in Toledo, and there are others. So this wave is not very obvious. But after 10 more years of observations, we really have this wave which better shows up. And the period was about the same. Again, there is definitely a certain error to this period, but it's not very large. Anyway, so this boring star is a binary, and this is the orbital period of this binary. It's interesting that we found also that star Psi Persei, which is a fourth magnitude star in Perseus, it has an orbital period of 179 days, again, based on V over R variations, and we were not able to do the radial velocity analysis because these are faster rotating stars. So we studied 12 systems, and now we can assemble more or less meaningful diagram which gives us a relationship between the full amplitude of the V over R variations and the period. So the stronger variations are produced in stars with shorter periods. And this is understandable because the components are closer to one another and gravitational interaction is stronger. Then if you move to lower amplitude stars, then definitely they should have longer periods, because again the components are further away from one another and the gravitational interaction is not there. There are some outliers in this diagram. For example, this star, 10 Cas, it's a B9 star, spectral type B9. And because of that, because of its low temperature, the line is pretty weak. And perhaps there are some other processes which affect the V over R variations, and it may not be a true orbital period. Anyway, that's at least the beginning. So if you just determine, if you determined the period, then you may be able to predict the amplitude of the V over R variations, or vice versa. Again, it depends on how much data you have, and with time we'll be accumulating more, and I believe we will populate this diagram better. All right, so to the conclusions. It turned out that detecting, measuring the VOR variations is a good method for detecting binaries, but again, it works in some intermediate objects, not very weak lined and not very strong lined. Then, in all the cases, the VOR variations are varying in phase with the radial velocity. And this can be explained by that hot spot or spiral moving in sync with the secondary component. Most of these results have been obtained from just the H-alpha line, but it turns out that you can use other lines, and this is especially important when the H-alpha profile is more complicated than just double-picked. It can be, again, triple-picked and can be single-picked. So H-beta line is also a good candidate, but it is not much weaker in the spectra of most stars, and only in the hottest B stars it shows a pretty big emission. And as usually, as Alex said, that observations need to be taken as frequently as possible. Maybe for this purpose of detecting orbital periods, you don't need to observe it several times a night, but just take a few individual spectra, which then are going to be summed up to produce a good signal-to-noise ratio. And in some stars, the H-alpha lines are very strong. And even at pretty low exposure times, they saturate. For example, I saturate, with my telescope, I saturate the H-alpha line in gamma cos in 10 seconds. So I usually take two series of spectra, one with longer exposures to get a higher signal-noise ratio in the continuum and in weak lines, especially absorption lines, and the series with very, very short exposures to have non-saturated H-alpha lines. And sometimes, since this stars also H-beta line can be saturated. So, and that's, I think I already covered that this method is good, but not for all BE binaries. So, with support from the amateur community, we will tackle these problems and we'll solve them. Thank you. Yes.
Sure. Thanks, Anatoly. Very nice talk. I'd like to ask you a few questions. About the central depression, if you could show the slide there. It's very interesting that you detected this in kappa track. Mm-hmm. That's the thing, right? We have a paper that's being written now with the models. No, the central depression that moves in phase.
It's epsilon Capricorn.
Epsilon Capricorn, yes.
This one.
So that's the one. So do you have the full? Can you show that it's moving in phase with the? Yeah. Because this is a prediction from the models, actually.
So this is the central depression of all 4 brighter Balmer lines. Yeah. And it actually was found first by Thomas Revenius. They did H delta line, but they analyzed H delta, H gamma.
Is this published or no?
This is published in Galaxies last year.
Yeah, because we are writing a paper now where this is actually predicted, right, from the models.
Yeah.
So we understand why this is happening. We can discuss later if you want.
Tell me.
Okay. About the Doppler tomography, a technical question. One of the difficulties is that you have to assume a little bit, you have to assume a Keplerian motion.
Yes, exactly. So we are finding that it's not fully Keplerian.
Yeah, that's the thing. It is Keplerian mostly, but it's non-circular, and that's the thing.
Yeah.
Is it possible in your method to put other velocity fields? It's easy. How easy would that be?
Well, I will need to ask my main collaborator because, I learned about it pretty recently, and I personally, probably you can actually, you can, I think I'm loud enough, you can assume something else, but it probably requires some modification of the code.
Yeah, no, because it's simply that in stars like this that perturbed by a secondary, it's Keplerian, but non-circular. It's meaning that their orbits are very elongated of the particles, and that's the thing. And then it's going to change the meaning of the Doppler tomography. That's a difficulty. Another final question: beta CMI, right? You put a very nice review there in yes, showing that there are two claims, that's binarity, and then Harman-Edge, the third item there.
There are previous determinations.
Yes, sure.
Which are wrong.
Which are wrong, yeah. Yeah, but then the third bullet there, you say that Harman-Edge said it is not.
Yeah.
Their arguments are actually quite strong, because the problem is that they say that this half a year period, and the period that you obtained is exactly half a year. It is because of telluric lines.
But here, well...
And that's the thing, and that's why I'm not saying that I don't believe that is a because we have another paper showing that it must be a binary for another reason, right? Yeah. But the problem is the period. And the fact that it's exactly half a year points strongly towards telluric lines contaminating the spectrum. It's very hard to remove. And that's the argument of Harman-Edge. So I'd like to hear your opinion about it.
Yeah. Okay, so when I look at my spectra with no correction of telluric lines, about 5 to 10% of them are really affected. And then you can use some templates from spectra of other stars. And basically you divide, that's kind of common technique, you divide the spectrum of your star by the template of telluric lines, which removes most of them. In that division, you are based on the strengths of these lines around. So you fit that, and it is supposed to fit other lines within the profile. So we did both. We did cleaning from telluric lines and without them, and it didn't change the result.
Okay, the thing is that what Harman-Edge says is that at the level you are saying, like, is 1% or so.
It's a few percent. It's actually 6.
So I'd like very much to, I think you've done it. So we have to start to believe it's 120, 82. It is like exactly half a year. It's probably, you believe it's a binary then?
Yeah. Oh. I do believe. But of course I'm suspicious about this period. But if you look at other binaries, there is no gap at 1 year or half a year. Recently, a few B stars with orbital periods of close to half a year have been discovered. By the way, we referred to that paper in our paper in galaxies. So there is actually nothing. And this period is not in the spectral window. All right, so we probably moved into a discussion between talks. Any other questions?
I was one of the observers on High Aquarium with Ernst Holden for a number of years. What is the future for observations of Pi Aquarii?
Yeah. So for Pi Aquarii, we just need to see. So we got 2 cycles already. Alex actually predicted some cycles.
Yes.
Yeah. And this is an observational. This is an experiment of the interpretation. So cycles are differently. I mean, a cycle is from no disk to disk and to no disk. So we don't have the full knowledge of what is happening, why it's happening, and how different those cycles can be.
Who should observers send the data to? Ernst or you? Or
now it's me.
Now it's you.
Because Ernst.
Yeah.
All right. Thank you. So let's move on.